I will be presenting two projects, one after another, because they all have a common background, side channel analysis. I will start with giving a common background for both of them, and then so that the second will seem like a bit shorter because the background is in front. So the first project I'll be talking about is side channel vulnerability and threat analysis with machine learning in focus. And starting with the background, I would like to explain what is a side channel attack. Some of you have been here last year and maybe heard my presentation, but still in brief, conventional mathematical cryptanalysis, when, for example, encryption system is attacked, the way it's done, you consider some mathematical relationship between the plain text and the ciphertext and apply some rules, try existing attacks, and so on. So you basically use math to prove that something is secure or not. On the other hand, any mathematical algorithm is implemented in a physical device, a system. It can be hardware, it can be software, but at the end it ends up in a physical device. And this device leaks signal. It's power, it consumes emission, electromagnetic emission, timing. We have physical things happening. And if these things are measurable, you can measure them and use them in your advantage and get some information which maybe allows you to weaken cryptographic protection or even break it. This is called side channel attack. Motivation for considering this type of attack. Side channel attacks belongs to the class of physical attacks because you do something on a physical system. The motivation for considering them is that in the near future we expect to have all the devices around us, smartphones, cars, smart things on the diapers which will send information to parents, change me. You know, there are actually scenarios like this. And these devices will be in a close physical proximity to potential adversaries who can be their users. User may be interesting to do something to his or her card, maybe to get some insurance or something. And probably you have all seen, I don't have to stop on it for a long time, things about Jeep being stopped, the brakes were affected on a distance. Maybe you have seen these headlines, or you have seen medical records being stolen, or health trackers being abused in some way. This is because a user can be a potential adversary for this type of attacks. So this is why we're considering this, because there are a lot of smart devices around us which use crypto inside. So the structure of MSB project, it's a 5-year project which started in the middle of March. It's two partners, KTH, I'm a computer scientist by PhD, and Thomas Johansson from Lund, who is a cryptographer. So it's a very nice merge of two types of expertise in this project. Both have one PhD student. The goal of this project is advance the state-of-the-art in side channel analysis using the toolbox of machine learning, because something like 5 years ago, people realized that we can use machine learning to make side channel attacks more efficient. And it's actually not just making them more efficient, and in fact enable something which was not possible. For example, the equipment you have seen on the previous slide, I can even return to show you. This equipment is the equipment we use to extract secret key from a commercial USIM card. The green thing is a card reader, which were manufactured, and the card you see stuck inside, and the other box on the side, it's chip whisperer, it's called. It's playing role of oscilloscope. It captures traces, synchronizes them, and saves them for us. So you need 4 power measurement to extract a secret key from a commercial USIM card. These are the cards sitting in your mobile phones. 4 power measurement the attacker needs to get the secret key. And then they can do everything. They can read your communication and everything. This is scary. And to put things in the perspective, previous methods needed 4,000 power measurements to extract the key from the same card. 3 zeros less, 3 orders of magnitude less. This is one thing, more efficient. And the second, some impossible things became possible. Let me give you one example. True random number generator, hardware true random number generator, sitting inside of many systems using crypto, for example, for generating nonces or for generating secret keys. Can we read bits generated by true random number generator using power analysis? We have one paper on it. It's not exactly 100%, 80% accuracy we read in predicting Hamming weight, but some of the attacks can be done efficient in this way. So not only deep learning resulted in these 3 orders of magnitude improvement, it also made some impossible things possible. And I know that nowadays we're all tired of deep learning and make jokes with it, but this is the case when deep learning really found its killer application, side channel analysis. It's actually amazing. So returning to the goals, we would like to advance the state of the art. Why do we need to do that? Because we want to understand possibilities and limitations, right? You need to become a good attacker yourself before you start designing countermeasures. One mistake one can do is start immediately from countermeasures. Then you will design something wrong. We need to have tools to test our countermeasures later. That's why attacks come first. Then we would like to develop new methods for assessment of side channel leakage and design countermeasures. That's, of course, the ultimate goal. The picture which you see on the slide, by the way, is the antenna we used to attack advanced encryption standard on a 15 meters distance. And this is the corridor which got blown up in Shista last week. It's exactly the corridor below which the bomb was placed. So all the windows in these offices where we sit lost glass. You probably heard about this explosion in Shista. It wasn't targeting KTH, thanks God. So results we achieved so far since March 2021, we published 2 journal papers, all of them are in THS, which are the top journal in hardware security, and 5 conference papers. I would like to focus my attention on the last one, stressed in red. We will present this result at Real World Crypto Symposium in March, later this year. This is called Breaking a 5-order masked implementation of Crystal Kyber by copy-paste. We like joking because one of the things about side channel analysis based on deep learning, not only it's possible, but sometimes it's amazingly easy. You will see that we will be really using copy-paste technique to do something which I would never expect to be possible. So let me tell you what is Crystal Kyber. It's a post-quantum cryptographic algorithm which NIST just standardized in July 2022. So this is a new standard. It's an algorithm which will be secure even if quantum computers, large scale, become possible. We don't know if it will happen, but if it happens, that will replace advanced encryption standard for encryption. And it's also key encapsulation algorithm. This is the way of exchanging the key between 2 parties. Maybe you heard about Diffie-Hellman. This is something which will replace Diffie-Hellman in post-quantum world. So this is a hot topic. And because NIST understands the importance of side channel analysis, they want to invest. So there is a lot of investment in doing side channel attack on this. And we are one of the groups who are trying to contribute to the state of the art. Right after NIST, NSA included Crystal Kyber in their suite of algorithms to be used for national security systems. So industry are starting to be preparing for the shift to post-quantum algorithms nowadays. That's why having this implementation secured, it's probably #1 thing of everybody working in related areas. So what we found is that existing implementations are not secure, even if they claim to be protected specifically against, to be secure against side channel analysis, and I will give examples of how you protect against side channel analysis. They are not secure. That paper I'm going to talk about, we went all the way to 5-order masking just to show that it's actually ridiculously unsecure. Let me tell you a few words which countermeasures are used today to protect against side channel attacks. One of them is so-called masking. You have your secret string of bits, and what you do, you create a random mask, typically generated using a true random number generator. For example, Cortex M4 has a hardware true random number generator as an IP. Very often chips have it nowadays. So you generate a random mask, and then you do XOR between your secret and the random mask. And then if you have a software implementation, that secret XORed with a random mask will be processed at some point, and then later the random mask will be processed, right? So you have them both. You can recombine the result together at some point, but you never have anything related to secret itself. It's always masked one. So the order, this is so-called first-order masking, because the number of masks you added, the number of random masks you added is 1. We broke 5th-order masking. We were just like going 2nd, 3rd, 4th, 5th, then we just ran out of time before the conference deadline, but I'm pretty sure you can go higher. I'll explain why in a second. And then the other countermeasure is shuffling, when you will execute instructions in a different order or shuffle bits of a key, because then you don't know which one is which. You know it's 1, you know it's 0, but what's the order? You don't know that. And we managed to break an implementation protected by both masking and shuffling, which was believed to be completely secure until we broke it. So let me explain why deep learning is so good in this type of things. Basically, deep learning is doing recognition of images. Power trace is an image. It looks like this cardiogram you get from your heart, something like this. It's an image. And what you do when you do training, you give these images to a classifier, and you train it. You say, this is the image, and we process here that bit or that byte or whatever it is you're using as a label. And in Kyber, the one I'm talking about, it's a public key crypto. And maybe some of you know that in a public key crypto, you use two different keys. When I would like to encrypt something and send to you, I will use your public key, encrypt it, send to you. You will use your private key to decrypt it. This is it. This is why we can attack Kyber. Because what we can do is we can take any message, use public key, which everybody knows, encrypt it and get a ciphertext. Then we can put the ciphertext to the device under attack. And because the public key, which we use, we know messages encrypted in the ciphertext. So we get labeled training data from the device under attack. This is not possible with advanced encryption standard. You can only do it to public key crypto. And well, if you say, what's the difference? Maybe you can use another device. This is not so, because another device will be slightly different from that device. This is called manufacturing process variation in VLSI design. Two identical chips never have exactly the same power traces. So if you can do training on exactly the same device you're going to attack, you achieve accuracy 99.99999, like 5 nines and a 0, which you will never get on another device. It will drop to something like 70. There are tricks to avoid it, but I don't have time for that. So basically, you can use device under attack for profiling, and this is the key. Then the second thing is, because it's a software implementation we're targeting, the secret XORed with a mask. You see on this slide M XOR R. J is a bit. We do it bit by bit, binary classifier, simplest to train. It's processed in one part of a power trace, and then later the random mask is processed. So what we do, we just gave both to the classifier. Look at them both. And the deep learning is powerful enough to not only recognize images, but also do simple operations. XOR is a super simple operations. So it can do bitwise XOR, 2 bits. And this is when 5 becomes important. When we did it for the first time for the first order masking, we said, let's see, how far we can go? Because Boolean functions grow exponentially as we add variables, right? So 2 variable XOR, can we do 3 variable XOR, 4 variable XOR, 5 variable XOR, right? And it becomes kind of complicated. And we tried this. And what we found out, at some point when we reach 4 variable XOR, we couldn't learn anymore. We were getting just random guess accuracy when you do nothing. Just we feed this trace, it cannot find it anymore. It gets confused. It doesn't see which points needs to be XORed. So then we were sitting, watching into these things. What you see on this line is power traces on the top, concatenated pieces which contain information. We know where it is. And then when you see on the second level, it's weights of batch normalization layers. Some of you who never do training, it probably doesn't mean anything for you, but this is just weights of a network, input layer of a network. And the peaks means this weight is important. This is where you should look. So you see on that picture, you see 5 peaks because we feed it's a 4-footer masking. Number of peaks is +1. So we look into the peaks and we say, can we just take the last peak and modify the model? Just copy-paste, because you see on that side for you, the last 2 ones are completely identical, because we copy-pasted. It's exactly the same shape. So we took the last piece from a trained model and created initial model for the next one. We call it recursive learning, just by copy-pasting. So we don't start from a random state. We start from that state, artificially created by copy-paste. It learned from the first time I pressed the button, just like this. Accuracy went out, from random guess to 90. That was amazing, probably the most amazing thing which happened to me this year. Last year, I should say, because it was really, we expected it, but not so easy. Copy-paste, that's why we put it in the paper. So this is all about that project, because that's the most exciting result. Now I'm passing to the next one. I don't have to give you an introduction. This is a project focusing on reconfigurable hardware. And one specific example of reconfigurable hardware is FPGAs, field programmable gate arrays. Many companies in Europe which are not producing things in large volume and cannot afford ASIC, application-specific integrated circuits, use FPGAs. What FPGA is just a gate array which you program. So the problem we solve, mathematical problem we solve here is we have a Boolean function and we map it into an array of blocks with up to k inputs, where k is the number of inputs in the lookup table. Nowadays we have like 6, 7 input lookup table, I believe. 6 is more popular. So then you have this array, and it's compiled into a bit stream, which is just 0 and 1s, like the binary you use in your software. And this bit stream is stored in a memory, typically flash, configuration memory. And then when this bit, at every power on, that bit stream will get compiled into the FPGA. So what is the attack you can do then if you want to steal intellectual property? Because it takes somebody $1 million to develop this design into the 0 and 1s. You can probe the bus and get it. It's called cloning. Xilinx and Altera both started to do encryption to protect intellectual property and use some other techniques. But even if you do encryption, you have to store secret key on device. And if I can get the secret key by side channel attack, encryption doesn't help. No cryptographic method help if a secret key is not securely stored. So that project is a 26-month project granted by Vinova. We started July in 2021. It ends August this year. It's 2 partners, KTH and Ericsson, Ericsson Research Group in Lund. What you see on this slide is the equipment we use for some side channel analysis on FPGA. You have so many FPGAs because we typically use more than one for profiling to fight manufacturing process variation, and more than one for testing, just to make sure that it's, sometimes things go wrong. It's always nice to test more. And then you have a Chip Whisperer. It's Chip Whisperer Pro because it has a large buffer. So the goals of this project are develop security assessment methods specifically targeting field programmable gate array technology and design countermeasures. So we have 6 patent applications submitting. It's a very recent field. So patents are just flowing. As you see, we have 1 journal and 3 conference papers published. I would like to focus on the last one in red, where we actually came up with the first countermeasure. We have a lot of attacks in the group. Usually you will have attacks all over my paper. This is the first time we felt confident enough to actually claim that this countermeasure is secure. We cannot break it ourselves. And this is a countermeasure which is based on a combination of a randomized clock and some duplication techniques I will show on the next slide. Let me tell you what is a randomized clock. Randomized clock countermeasure is as old as side channel attack themselves. Person who introduced side channel analysis, Paul Kocher, he introduced it in 1999. Same year they had a patent on clock randomization. Clock randomization, basically, it's simply your clock period will not be stable, but it will be kind of changing. Sometimes less, sometimes more. So on the first picture, you see a power trace with a stable clock, like stable peaks, like repeating pattern. The other picture shows you unstable clock. So that they will be like narrower, wider, and so on. So until recently, last year when we published the paper, it was believed to provide enough protection against side channel analysis. We managed to break it using deep learning techniques and oversampling. We sample 100 points per clock cycle, then do some synchronization, and then we can break it. So it's good for him that patent expired a few years ago, because the patent is 20 years. So what we proposed instead, as we were breaking, we realized that what would prevent us from breaking it was if we have a block working in parallel with a main block. Just as this, very often simple things work, in fact. I like simplicity. Simplicity is beautiful, I think. So what we did, we duplicated advanced encryption standard and have 2 randomized clocks. We use resources, available resources in FPGAs to create 2 randomized clocks. Each of them is controlled by their own. This simple countermeasure we cannot break. We tried for many months already, and we are at the moment quite confident because it's actually not some hardware techniques, but it's actually math behind. But to be able to break them, you have to be able to distinguish peaks you get from one core from the peaks you get from another. Imagine they're colored, blue and red. You see peaks together. How do you know which one is which? Brute force search doesn't work. It's 2 power number of traces. If a number of traces is 100, good luck. It's just impossible. So it's based on the combinatorial blow-up below the attack, which we believe is most efficient. Maybe somebody will come up with better. But let's just present you our results. To break unprotected implementation of advanced encryption standard in this FPGA, we need, on average, 116 power traces. If it is duplicated with a stable clock, it doesn't get easier. It doesn't get much harder. It's like roughly double to 120. If duplication is one randomized clock for both cores, it also doesn't work, as you see. It gets a bit more complicated, but it's not enough. And we cannot break today two randomized clocks. Although it's so simple, we cannot really break it. And the beautiful thing beyond this countermeasure is it's simple. And simplicity is beautiful, because if you want to implement masking, this 5-order masking we broke, it's so complicated. It's such a high probability that somebody will do something wrong, that designer will actually implement it wrongly. Here you just duplicate it. It will take you 10 minutes to take a core and duplicate it. That's first. Second, application independence. You can duplicate anything. Advanced encryption standard, Crystal Kyber. In fact, we are coming out with protected implementation of Crystal Kyber publicly available because people need it. We duplicated it. It takes 5 minutes, and then you have to do the randomized clock. You can duplicate anything. You can duplicate deep learning models if you want to protect them against side channel analysis. And you probably want it, because in the same way, I could potentially steal weights from your networks, and this is intellectual property, which people started doing it, in fact. It's the next big thing in side channel analysis. Glitch immunity. It's one of the problems with duplicating and having a stable clock is that you cannot really perfectly synchronize two units. You'll have glitches in between, and this is used a lot to break hardware implementations which are using redundancy. Randomized clock solves this problem. And finally, universality of coverage. We covered everything. For example, masking just covered the parts which are believed to be secure today, but maybe tomorrow somebody will come up with the attack. For example, almost nobody covers key generation part because they believe that you cannot exploit it. Maybe that will change tomorrow. We just duplicated everything. So we are potentially secure against attacks which come tomorrow, unanticipated attacks, which is great, right? So to summarize, the current status in the field is that deep learning side channel analysis are very powerful. This is a very powerful class of attacks. Be aware of that. They can overcome traditional countermeasures, masking, shuffling, combined ones, randomized clock, and many other countermeasures we broke. We introduced countermeasures suitable for hardware implementations. We are working on the ones for software. So far, everything we come up with, we break in 3 months. We had so many ideas, so many unwritten papers, because like some new ideas come and we break it. That's something we want to do. Maybe next year when I report you, it will be done. We will see. And I would like to finish thanking all the agencies, not only MSB and Vinnova, but for example, Vetenskap Rådet, which were the first funding agency in Sweden who gave me money and trusted in me that it's an important topic to invest. I ran out of this project already. It's finished, but I'm still grateful to them. Thank you for your attention.
Thank you very much.